Predict the major product in each of the following reactions. So these reactions all involve the addition of first the protonation of a double bond and then addition of some nucleophile. In this case, it's water in A. And in B and C and D, we are adding a halide to the carbocation. But first things first, let's look at the carbocation that results when we add acid across the double bond. So I'll just redraw A here. And so we have 3 carbons, 1, 2, 3, and then a double bond, and a methyl and an ethyl. So it's much easier for me to see. Actually, I think I put too many carbons in there. It's easier for me to work these problems with skeletal structures. So we're going to first add, and I'll just put this as H+, add H+ across the double bond, and we have 2 possibilities. We can either make a secondary carbocation if we add here, or a tertiary carbocation. And the tertiary carbocations are much more stable, so we'll add the proton to this carbon here, and that will give us a tertiary carbocation here. And then water will add OH2, and we will get OH2, and then write my arrow here, and then that will lose a proton to give us our alcohol, OH. And we don't really need to show what's going on there, but we could, since we have water, H2O, we could just do this, draw that curved arrow, and then that one, to show that we're pulling off a proton, making H3O+, and our alcohol here is the major product. So let's look at B. Here with B, we also have a situation where we're adding, to a double bond, HBr, and we can draw these curved arrows here. To give us our tertiary carbocation. So this is, here's this proton here, and then we added, just so we can kind of keep track, we added this hydrogen to this carbon, and that gave us this carbocation, and now we have Br minus, so Br minus, and that will now add to the carbocation here, and we'll get our product. So here's our product here. Our major product has a bromine attached to the tertiary carbon. So this again is Markovnikov addition in all of these cases. And let's look at C here. So in C, we have a slightly different situation. We can't form a tertiary carbocation right away. And so let's just look at what happens here if we, so this is C. If we pull off a proton from HBr with this double bond, we can either make one of two carbocations. Both are secondary carbocations, so they're equally stable. So we could make this one, or we could make this one. And if we make this one, then the bromide, Br minus, will attack and or will add to that carbon, and you'll get a bromine there. If the bromide adds to this carbocation, another secondary carbocation, so both of these are secondary. This one's secondary and this one's secondary. So they're both relatively had relatively the same stability, and therefore are equally likely to form under these conditions. So we have now bromide adding to this carbon, and so that's, in both of these cases, bromide adds to a secondary carbocation, but notice, since we have this methyl group here, we are making two different, essentially constitutional isomers. So this is a case where the regioselectivity is not great. It's not good enough to give us a single one of these products. But in addition to these, we also have an opportunity for a hydride shift. So instead of bromide adding, since we have a secondary carbocation next to a position that could be a tertiary carbocation, if we move something, in this case a hydrogen or hydride, that's a hydrogen with its pair of electrons, so that's a hydride. If we move the hydride over to the carbocation, we'll make a new carbocation. So this is yet another pathway for this reaction, and that will give us a new carbocation here. This hydride has shifted over here. Now we have the hydrogen there, and bromide can add now to the tertiary carbocation, and we will get yet a third product. So this sort of highlights that these reactions are often don't proceed with perfect selectivity, and when you have carbocations, you have the opportunity for lots of shifting to take place. And then if we look at D here, and let's just do it on the page, on the problem. So we can add across this double bond, and since there are two equivalents of HCl, we'll add across the other double bond, and we'll make the two carbocations. And let me just count the carbons: 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. And we'll end up putting those carbocations on the secondary carbons, much more stable than if we generated the carbocations here on the termini, which would be primary carbocations. And then the chloride ions, Cl minus, Cl minus, will just add to those carbocations, and we will get our product here with two chlorine groups, a dichloroalkane here.